Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. We have learned that the derivative of ln of x is 1 over x, and up until now, we've been taking that as a fact. But why is that the case? What else can we infer from this rule, and what power do we hold when we have a mastery of logarithms? In this video, we're going to unpack a few of these relationships between logs and derivatives. And before we dive in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. First, we're going to prove that the derivative of ln of x is equal to 1 over x. And because we have unlocked implicit differentiation, this proof is actually pretty simple. We're going to start by letting y be equal to ln of x. This means if we rewrite this into the exponential form, we would get e to the power of y is equal to x. And now we're going to take the derivative with respect to x on both sides of this equation. So we're going to go d by dx of e to the y, and that is going to be equal to d by dx of x. Now remember that y is still a function of x. So on the left-hand side, when we take the derivative of e to the y, we have to remember to use chain rule. So that's going to be e to the power of y multiplied by dy dx. And then on the right-hand side, that is equal to 1. And now if we isolate dy dx, we get dy dx is equal to 1 over e to the power of y. But notice that e to the power of y is just equal to x, which means we can go ahead and substitute that in. So which means this is equal to 1 over x. And since y is equal to ln of x, we have now proven that the derivative, so d by dx of y, which is ln of x, is equal to 1 over x. Now, we've been working with natural logs when it comes to derivatives, but logs aren't always written as natural log. We know that there are multiple bases possible when it comes to logarithms. So how do we tackle these other different bases? Here, we want to show that the derivative of log base a of x is equal to 1 over x ln of a. To show this, we're going to go back to our log laws and pull out our change of base rule. And the change of base rule says that if we have log base a of b, this is equal to log base c of b over log base c of a, where c could be any number. Therefore, the derivative with respect to x of log base a of x can now be rewritten as d by dx of ln of x over ln of a. So here we have chosen our c to be e, which means we get to use our natural log because we already know what the derivative of ln of x is. And now since a is just a constant, ln of a is just some number, which means we can go ahead and pull it out in front of the derivative. So this is going to be 1 over ln of a times d by dx of ln of x. And the derivative of ln of x is just 1 over x, which means we get this as ln of a times 1 over x. So therefore, our final answer here is 1 over x times ln of a. And now let's take a look at how we can put this new rule into practice with a warm-up derivative before we move on to a new strategy that we're going to be showing in this video. Here, we want to find the derivative of f if f is equal to log base 2 of sine x. So putting what we just learned into practice, that means f prime of x is going to be equal to 1 over sine x times ln of 2, and then we need to multiply this by the derivative of sine x. So that is going to be times cos x, which means this is equal to cos x over sine x times ln of 2. And we can combine cos x over sine x into cotangent x, so which means our final answer here is cotangent x over ln of 2. Perfect. That wasn't too bad. It's just another rule that we can use in conjunction with all the other rules that we've done so far in this chapter. Now let's take a look at what is this new strategy that I just hinted at. So here we want to find y prime if y is equal to, and that looks like a pretty monstrous expression. So you might be thinking, well, I don't see any logs here. Why is this quotient rule and chain rule mess even here? Well, logs can help us simplify this process if you recall your log laws. And the strategy that I'll be showing you here is called logarithmic differentiation. And this is unlocked thanks to implicit differentiation. So what you do is you're going to take this original equation, and then you're going to apply the natural log to both sides, which means you're going to get ln of y is equal to ln of that expression on the right-hand side. And the reason we want to do this is because we have log laws in place that can help us simplify this right-hand side. So if you recall, if we are logging an expression where we have a fraction, this actually is equal to ln of the numerator minus ln of the denominator. And then we can simplify this one step further because we can peel the power down in front of our log. So we get 2 times ln of x plus 1 minus 1/2 times ln of x minus 2. And this is equal to ln of y. And now that our equation has been simplified, we can go ahead and take the derivative with respect to x on both sides of this equation. So that means we go d by dx of ln of y is equal to d by dx of this entire expression on the right-hand side. So 2 times ln of x plus 1 minus 1/2 times ln of x minus 2. The derivative of ln of y with respect to x is going to be 1 over y times dy dx. And then on the right-hand side, this is going to be 2 times 1 over x plus 1 minus 1/2 times 1 over x minus 2. And now the last part is just to isolate dy dx. So we get dy dx is equal to y times 2 over x plus 1 minus 1 over 2 times x minus 2. And this would be our final answer. And finally, for our last example in this video, we're going to take a look at our power rule. So we've used this rule many times in this playlist, but we've never proved it. And one of the ways that we can prove it is with logarithmic differentiation that we just learned. We're going to start by letting y be equal to x to the power of n. Then we're going to take the natural log of both sides, which means ln of y is equal to n times ln of x. So this is already with me using the log law where I pull this power down in front of our log. And now we're going to take the derivative with respect to x on both sides. So we get d by dx of ln of y is equal to d by dx of n times ln of x. The left-hand side, we're going to get 1 over y times dy dx. And then the right-hand side, we're going to get n times 1 over x. Isolating dy dx is going to give us dy dx is equal to y times n over x. And now we can go ahead and do our substitution because y is equal to x to the power of n. So this is equal to x to the power of n times n over x. And finally, simplifying this gives us dy dx is equal to n times x to the power of n minus 1. And again, because y is equal to x to the power of n, we have thus proved that the derivative of x to the power of n is equal to n times x to the power of n minus 1. And now let's do a quick recap of what we covered in this video. We have now generalized a log rule for any base a. The derivative is 1 over x times ln of a. The ln a term acts as a scaling factor, and that was derived from the change of base formula. We learned a new technique called the logarithmic differentiation. This technique uses log properties to transform complex products into sums and messy quotients into subtractions before we differentiate. And we have finally proved the very first derivatives we've seen in this playlist, which is the power rule, with the help of logarithmic differentiation and implicit differentiation. And now it is your turn to give this a try. Can you find the derivative of this function on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.